Our first talk is from Vladimir, talking about generating 1 terabit of traffic on commodity hardware using T-Rex. Anything with dinosaurs we love, right?
Yeah. Yeah. So yeah, thanks for having me. Yeah, sorry, it's been a while since I gave since last time I gave the public talk, so I might struggle a little bit with time management. But yeah, I'll try to leave a few minutes in the end for questions and so on. Yeah. So. How it all began? Well, I live in Switzerland. I really like to tinker with hardware, especially with exotic hardware. I had a background of sysadmin SRE style, so 15 years of experience roughly. I really would like to have some sort of a side hobby project that would be really, really close to the hardware itself. Yeah. And at the beginning of the project, I didn't have a lot of experience with networking. I mean, I know the theory. I haven't actually did a hands-on experience for a while. Yeah, and in mid-2023, the ISP where I live said, hey, like we actually start providing 25 gigabit home internet for you. So I decided, like, why not to upgrade? And suddenly, like my home network and home hardware became a bottleneck. A good friend of mine suggested to talk to Pim van Pelt, as he was doing a lot of things and a lot of stuff around performance testing and so on. And Pim mentioned that he have a project and idea of doing a terabit router. So building a load generator for that sounded like actually ticking all the boxes for the hobby project. So yeah, or TLDR, like paraphrasing the movie, I was so preoccupied with whether I could that I didn't actually stop to think if I should do that. So roughly, like I need to come up with sort of like what are the constraints for the hardware that I'm building. First obvious one is actually PCIe bandwidth, like servers with like Gen 3 for x16 slot, you roughly would get enough bandwidth for a 100 gigabit network card. For Gen 4, double that. For Gen 5, well, double of the Gen 4, so roughly 2 times 200. Then next obvious bottleneck is actually how many PCIe is available on the platform. And here comes the problem. Desktop platforms are cheap, but they are not really, like you don't have a lot of PCIe lanes. Like in theory, you might get 28 lanes on modern desktop hardware, but good luck finding a motherboard that gives you like more than x16 slot. Like x16 plus x4 or something like that is what you get. So server or workstation kind of platforms, like you have 80 or 112 lanes on Xeon's previous generation, because that's when the whole thing started. You have 128 lanes on AMD EPICs, or like 96 on a smaller EPICs, and basically, yeah, those would be the obvious choice there. Another constraint is money, because that's a hobby project, therefore no sponsorship. All the hardware, like I pay with my own money out of my pocket. Therefore, it must be as cheap as possible, and like I wouldn't actually refrain from buying used hardware if I can like fix some of the problems. Another problem is like, again, comes from the money constraint, that I really would like to reuse the same thing for like testing the VPP and run VPP. And here comes the interesting part, that Intel supports DDIO, which is their technology of basically that PCIe device can actually, like you can bypass the RAM and get the data directly to L3 cache. And they have it since like Xeon E5 V2, E7 V2, so for quite some time. AMD supports a similar one as DCI since Zen 5, and at the moment when the whole thing started, Zen 5 was basically not available on the market, like not for the consumer at least. And another constraint, like I wanted to use small packets because otherwise it's just not fun. Like, and therefore the idea is to start using the workstation version of Xeon. So start with something simple with 16 cores, maybe get another one or upgrade when it will become a bottleneck. And because of the platform, like I actually have quite a few of PCIe slots, like 16 slots is something easy that you can get on the market. And therefore, in theory, it should be enough to get like 1.3 terabits per second of theoretical performance from a single machine if I would go for Gen 4 cards, which are just cheaper. Another problem, not all the network cards are equal. Like unfortunately, there is not a lot of good information or good source of information about what they can do. Vendors, for some reason, really hide this in various documents and so on. But like DPDK performance reports allows you to get some idea of what you can get. So like Mellanox or NVIDIA ConnectX cards depends on the generation on the card. Theoretical performance that they claim is 148 to 268 megapackets per second. On Intel, it's slightly lower. They show like 112 to 228, and Broadcom actually haven't updated their performance reports for a while. They, for some reason, don't use the latest generation, and therefore, yeah, like 100 something. And yeah, availability and the prices on the used market also varies a lot, and that's yeah, yet another problem there. So therefore, the idea is to start with a mix of whatever I can get from like ConnectX 5, 6, or 7, because there is a plenty on the used market. They are relatively cheap. Start simple with just loopback tests, and then like try to expand from that. Also, there is a lot of cheaper blue fields for whatever reason on the market. So like maybe look at those. And because I went for the 16-core platform, I mean, hyperthreading might be useful. So I would also try to investigate how that affects the performance. So software side is relatively simple. Like there is a lot of open source testing platforms, but I went with Cisco T-Rex because that seemed to be the most mature one. They also have very nice claims. So like basically from their website, they claimed it to be a realistic traffic generator. It uses DPDK, so it should be fast. They claim to be able to generate 200 gigabits per second. So yeah, a little bit not enough, but we'll see about that. And you can actually write custom generators. They use SCAPI under the hood for that. There is so here comes the problems. Like you don't really need to look at the graphs or like try to read the numbers. It's not really relevant, but that's basically how the text user interface of the T-Rex looks like. And you can notice that it doesn't really scale well. It provides a very nice representation. It looks pretty, but for whatever reason, it have few limitations on how much ports it can display and so on. So, like, yeah, like I needed to do a little bit of patching here and there to actually get like make it display more ports and so on. And even then, it was not that easy to use. They have a stateless graphical interface, which is slightly on the heavy side. Also, it's like last time it was updated, it was like 6 years ago or something like that. So I decided, yeah, like maybe I wouldn't even try that. And there is also a bunch of scripts around load generation, but they are not real time. So like the T-Rex load test viz is actually a very nice set of scripts, very nice project, but it's not real time. So my solution there was just to like, okay, let's try to write the Prometheus export and display all that stuff in Grafana, because yeah. Here comes more problems. T-Rex have relatively nice documentation. Unfortunately, it's not complete. In some cases, you just have method names and guess what they do. You have the parameters by name. Again, try to guess what they are doing, what kind of results like you will get, and so on. Yeah. So another problem is some of the API were like, so getstats API is one that they suggest to use for getting the performance counters, and it requires, for whatever reason, write access. Text UI doesn't require write access, on the other hand. But text UI is relatively large. It handles a lot of corner cases and not that easy to read. But unfortunately, I haven't found any other way to do that except like reading what text UI do, try to experiment, try to like iterate fast. So like basically run the load generation and see how I can what I can get from that. And in the end, actually, like it took me several hours to write some sort of a proof of concept exporter. It's unfortunately I needed to use some undocumented APIs because text interface actually use direct field access for getting some of the data by passing the right lock, grabbing the right lock. But it kind of works. So I mean, it displays data, it gets them accurately enough. So yeah. And of course, it's like I put everything on the GitHub. It has some rough edges. It's like if you restart the T-Rex server, it won't reconnect. But yeah, I mean, somebody can fix that if they would be too annoyed with that, or maybe eventually I will fix it. Another problem. The load generator that comes with like the set of scripts that comes with the T-Rex, they don't cache the data that they are generating. Therefore, you can, so it requires too many cores for doing like meaningful work. Luckily, like scapI helps in that sense. It's like, so there are multiple talks like during FOSDEM, like there was a talk at FOSDEM 2024. There was a PIMS talk as well that mentioned how he solved this problem. Basically, the solution is simple. You write your own generator. It's like 18 lines of meaningful code and a little bit of boilerplate around that. So yeah, just like for my case, it's like just using UDP was good enough. And again, all the scripts are on GitHub if somebody wants to have a look at that later. So the network cards, like ConnectX 5 and 6, both claims like PCIe Gen 4, 2 times 100. So they should perform the same. Unfortunately not. That's the part where the vendors doesn't explain exactly how different they are, and unfortunately you need to test it for yourself or carefully read the reports online to find the performance. And basically, when I ran the tests, ConnectX 5 reached roughly like 130 megapackets per second. ConnectX 6 reached 180. There is some weird behavior, like you have a plateau of like from basically 2 cores per card to 5 cores per card for some reason, and there is no literally no explanation over that. But yeah, my conclusion there is I would try to prefer the later generation if possible. And same thing is with ConnectX 7 and Bluefield 2. Bluefield 2 roughly performs similar to ConnectX 6. It's slightly worse, but just slightly worse. ConnectX 7 on per slot basis is really good. It's better than ConnectX 6 by like 20 or 30%. Unfortunately, it's too expensive for me. And Bluefield 2 is for some reason extremely cheap right now on the used market. So yeah, and that's the conclusion there, that for network cards, I would try to prefer like ConnectX 6 and Bluefield 2s, completely avoid ConnectX 5, and yeah, if I can get ConnectX 7 for cheap, yeah. There is another problem while I was testing this. Like I wrote a simple script that was basically ramping up the performance, and I noticed one interesting behavior that actually kind of limited what I could have tested there. When I'm close to 100% CPU utilization, there is a huge difference between what is the target for the T-Rex and what it actually generates. So there is still no packet loss at like 180 megapackets per second on this screenshot, but the target is set to 240. And it have various checks that actually limits the amount of, so limits the target so you cannot go above what bandwidth would allow you to. So because of all of that, the hyperthreading, there is a lot of controversy about that topic on the internet, because if you ask like T-Rex maintainers, they say just don't use it. If you ask literally anyone, they would say just don't use it. However, with 16 cores, I kind of don't have a choice. So, like, at least I should try. Again, I ran the same benchmarks, and yeah, basically, at least on the Sapphire Rapids machine that I was using, depending on the load, it actually gave me roughly 30 to 40% of a single core performance, which, but the price was that it became less predictable in a sense. But again, for my tests, that's kind of good. So the final setup, I started the first attempt, 5 threads per network card, using a mix of cores and hyper-threading, like ConnectX-6 and ConnectX-7, and the mentioned before 16-core machine. At the first attempt, unfortunately, from the single machine, I haven't been able to reach anything near terabit. It was roughly 600 gigapackets per second, roughly 600 gigabits of 128-byte packets, and there was nothing else that I tried made it scale above. So I stepped back a little bit, tried to fine-tune the things. I basically locked the turbo frequency at 4.7 gigahertz, which is like the max for the CPU. So basically overclocking it a little bit. I also recompiled T-Rex with Intel's compiler because, I mean, if it can give me a little bit of performance, why not try it? And my result in that case was still far from a terabit. It was 850 gigabits per second from a single machine, which is not that bad, but I would prefer slightly better than that. And yeah, and that comes to the trying to analyze what went wrong. The single card works just fine. When I add traffic, the performance drastically drops, and it drops in a very interesting way. It mostly dropped on the cores that are not related to the network card where I'm increasing the performance. So I increase, I put 50 or 60 megapackets per second load generation on card 1, and the performance on card 2 drops. So it's looks strange. And unfortunately, I don't have the answer that I can prove right now, but my theory is that modern CPUs are extremely complex in that sense. You have the multiple clusters. The PCI root complexes belong to specific clusters. You have all kind of mesh networks between, and even Intel CPUs, while they would try to avoid that, Sapphire Rapids is 4 clusters anyway. So as far as I understand, that could be the potential cause. It's probably a bottleneck somewhere on the fabric. And maybe with more careful placement of threads, I can actually work this around, or probably having more cores per cluster. So the easy solution was to actually add the second machine. So I went for the same same 16-core Xeon. So put less network cards in each machine. And that actually allowed me to get 1.1 billion packets per second combined on both machines. So 550 per machine, roughly, at 0 packet loss. And yeah, and of course, if you increase the packet size to 128 bytes, you basically get a little bit more of traffic as well. So we can achieve 1 gigapacket and 1 terabit at the same time. Yeah, but that's kind of easy. I potentially can replace 2 machines with one with more cores. And unfortunately, the drawback is the power consumption. I kept the overclocked machine still overclocked, so it consumed 870 watts, and the other one was just running on stock at 630. There was slight difference because of that, of course. Yeah, and basically, you can actually build a load generator on relatively tight budget because, 16-core Xeon is not that expensive. It's roughly 3.5 thousand euros per machine at retail prices, and probably 1/3 of the price goes to RAM, and I probably could have saved a little bit there. Yeah, here I'm obliged to say by my wife that she doesn't agree with my definition of tight budget. Yeah. Yeah. It's actually interesting that T-Rex have very conservative claims on their website. They claim that they can generate 200 gigabits from a single machine, while like this machine was able to do 800. So basically 4 times more. In terms of the per core performance on modern machines, you can expect basically like 35 million packets per second from each core. And hyperthreading helps a little bit. It basically adds like 1/3 of a core, basically. And in some cases, actually, it was interesting that vendor compiler actually helped a little bit as well. Basically had 5 or 10% more performance by just using Intel compiler. Yeah, and I actually have quite a few plans on the future on how to improve on all of that. I want to actually find the root cause of my problems with crosstalking and so on and prove my theory or actually find the actual one. I want to test on the AMD machines. I also want to eventually try to migrate everything to the Bluefield too, because it actually uses ARM CPUs and probably should be able to do 100 gigabits on its own. And yeah, and obviously try to fit it in a single machine. Yeah, so thank you for your time and questions.
Thank you. Have we got any one-word answer questions?
No.
No, that's to him.
Okay. Yep.
Yeah, that's the second question. Will you be coming to Sona?
Maybe.
Okay. Does anybody else have a one-word question? No. Thank you again. Great talk.